an important thing here is we're interested in doing some sort of chemical changes. How can we actually go back and forth from one phase to another? And how much, how much thermal energy do we need to be putting in the system in order to carry out these processes? So let's say that, so this is what we call, a heating curve. And this will say, to get the numbers right, we'll use water at 1 atmosphere. So you'd have a different shaped curves at different pressures. And so it's got water at 1 atmosphere. And say we start off in the ice form. And so we'll be heating it there. And the slope of, if we're plotting heat added versus temperature, the slope will be 1 over the heat capacity. Remember, heat capacity is heat over temperature. We're plotting temperature by heat. And so the slope will be 1 over the heat capacity. So as you go up, it'll be, you add heat, it'll be the temperature will be generally increasing until you reach the point where you have, it would reach the melting point. And at that point, as you add heat, that heat, assuming that it's, relatively well mixed and you don't have, a relatively large system so that there's a spatial imbalance in where you're adding the heat, assuming the heat is added uniformly, then all the heat goes into not heating it up more, but changing the phase, melting it from ice to water. And so how much heat do you add? Well, the enthalpy of fusion, that's literally what it is, the heat it takes to go from ice to water. And so then once it's entirely melted, then you'll start heating it up again. The slope there will be 1 over the heat capacity of water, and heat capacities of solid and liquids are relatively similar. Okay, so you heat that up until you get to the boiling point, and at that point you start converting water to steam, liquid water to steam. And how much heat does that process take? Well, it takes the heat of vaporization. And then finally, to the point that it's entirely steam, as you heat it up, that heat capacity is generally lower than the heat capacity of ice or water, and then it continues to heat up there. The slope will be steeper because the heat capacity is smaller and the slope is still 1 over the heat capacity. So that's generally what a heating curve looks like. You heat till you hit a phase transition, then it's flat. Then you heat, you add more heat, the temperature goes up till you hit a phase transition, and all the heat goes into converting it into from one phase to the next phase. All right. So that's just reminding you that, the heat added is the heat capacity times delta T. So the delta T will be 1 over the heat capacity times the heat added. So that's what this looks, but what about the quantitative numbers? Let's go to that as well. So how much heat is released when we have 75 grams of steam at 100 degrees C and it's cooled to ice at minus 15 degrees C? Well, for water, we got some information: the enthalpy of vaporization, enthalpy of fusion, molar heat capacity of liquid water, and the molar heat capacity of ice. Okay, so we're given molar heat capacity, so we're gonna have to convert here. This is 75 grams H2O times 1 mole of H2O over 18.02 grams of H2O. As the grams of H2O cancel, we get 4.16 moles of H2O. So this is about 4 moles water. So what are the steps we have to go when we're cooling down the steam to ice? Well, one is going to be the vapor to liquid phase at temperature equals 100. Now, once it's a liquid, then we have to cool it down from temperature equals 100 to T equals 10. Then in a third step, we go from liquid to solid, T equals 0. And a fourth step, we go from solid at T equals 0 to solid at T equals minus 15. So there's 4 steps that we have to take into account. And we're releasing heat, right, because we're going from a high energy state steam to a low energy state ice. Okay, so for the first step, well, the first step is simply the condensation. We don't have the heat of condensation. Yes, we do. It's minus the heat of vaporization. So 1 is pretty easy. That's minus 40.67 kilojoules per mole. Great. All right, so on the second part, we need to look at the heat released as we cool. And we'll just do everything on a molar basis and then multiply by the number of moles at the end. We've got the heat is going to be the heat capacity times delta T, right? So the heat capacity is 75.4 joules per mole Kelvin. And we have to, again, we're looking at the heat capacity of water because we're cooling the water at this point. 1 kilojoule, 1,000 joules. So the joules cancel. And we have minus 100 K because we're going down in temperature. And that would be minus 7.54 kilojoules per mole. So step 2 is minus 7.54 kilojoules per mole. Okay. And next for process 3, well, process 3 is simply, this is 2, process 3 is simply the heat that's released as the water freezes, which is minus the enthalpy of fusion. So we actually don't need to do any calculation there. We can just write out this 3 minus 6.01 kilojoules per mole. Freezing is the opposite of fusion. Fusion is kind of annoying because you think of like cold fusion, nuclear fusion. This is just the melting of some solid substance. This is the way it's tabulated. And then in our fourth part, we're going to be cooling the ice down. So again, Q is equal to C delta T. And so that is 36.4 joules mole Kelvin times 1 kilojoule, I'll convert it to kilojoules, 1,000, times minus 15K. And so the K's cancel, joules cancel, and we get minus 0.55 kilojoules per mole. And so minus 55 kilojoules per mole. Step 4, we add up all those 4 steps to get minus 54.77 kilojoules per mole times 4.16 moles, and that will equal minus 227.8 kilojoules. All right, so that's the amount of heat released when we condense this steam and freeze it to ice at minus 15 degrees C. And one interesting thing to notice here, you notice that the biggest factor by far is the heat released by condensation. And this is pretty typical. First of all, you get a lot of heat in phase changes. So this is really important in a lot of chemical engineering practices because a lot of separations involve phase changes, which involves heating things up a lot, which you want to avoid as much as possible because that takes a lot of energy. And this makes sense because what we're doing is we're pulling the molecules of the liquid completely away from each other. If we're just looking at the heat of freezing, then you're going from a lower energy state, a solid state, to a not that much lower energy liquid state, because you're only like partially moving out of the wells. You're mostly staying connected to the other molecules. And so it's not that much higher in energy. Then the heat required to actually raise the temperature of the molecules, they're jiggling a little more, but that's not nearly as big as going through a phase change. So the phase changes are usually big energies, and the biggest is definitely the phase change from liquid, where they're still mostly stuck together, to vapor, where they're not stuck together at all. You have to really put in a lot of energy there. So that's why the heat of vaporizations are bigger than the heats of fusion. Okay.